Welcome to today's lesson on the logistic function and its remarkable ability to model threshold phenomena across various scales in physics. The logistic function provides a powerful analogy for understanding nonlinear transitions from one state to another, whether we're looking at quantum physics or planetary atmospheric systems. Let's start by understanding the logistic function itself. The logistic function is given by f of x equals 1 divided by the quantity 1 plus e raised to the power of negative alpha times the quantity x minus 1. This creates what we call an S-shaped or sigmoid curve that transitions from 0 to 1 as x increases. The logistic function has some important features to understand. First, the midpoint of the transition occurs at x equals 1, where the function equals 1/2. Second, the parameter alpha controls the steepness of the transition. A high alpha value, like the red curve, creates an abrupt, almost instantaneous switch. A low alpha value, like the blue curve, results in a more gradual transition. What makes the logistic function so powerful is that it serves as a universal model for systems that undergo a nonlinear transition from an off state to an on state. The function effectively models any system where a critical threshold must be crossed to trigger a significant change in behavior. Let's explore some real-world examples of these threshold phenomena, starting from the smallest scales of quantum physics all the way up to planetary systems. Let's begin at the quantum scale with the QCD mass gap, a profound example of a threshold phenomenon. QCD, or Quantum Chromodynamics, is the theory of the strong nuclear force that binds quarks together. The QCD mass gap refers to the minimum energy needed to create observable particles from the strong force field. This threshold is approximately 135 megaelectron-volts, which is the energy needed to create the lightest hadron, the pion. The QCD mass gap perfectly illustrates the logistic function model. Below the energy threshold, the strong force is effectively off. Quarks and gluons cannot be observed as free particles. They're confined within composite particles. As we cross the energy threshold, there's a rapid transition. The force switches on, and we can observe its effects through the creation of hadrons. This mirrors our logistic curve. Below the threshold, the function approaches 0. Above it, the function approaches 1. And at the threshold, we see a rapid, nonlinear transition. Now, let's move to a much larger scale and examine Earth's global electric circuit, another system that exhibits threshold behavior. The global electric circuit is a continuous electrical current that flows between Earth's surface and the ionosphere. This circuit is powered by approximately 40,000 thunderstorms occurring daily around the globe, which act as generators of charge. A fascinating example of threshold behavior in the global electric circuit occurs during thunderstorms. Have you ever heard that your hair standing on end can be a warning sign of an imminent lightning strike? This is a perfect, real-world example of crossing a threshold. When the electric field strength in the atmosphere reaches a critical threshold, the repulsive force between like-charged hair strands suddenly overcomes gravity, causing your hair to stand up. This abrupt, visible change signals a dangerous threshold in the atmospheric electric field. You've entered the on state of our logistic model. Now, let's look at how the concept of a threshold or boundary layer connects to ancient understanding. In ancient cosmology, there was a concept called the firmament, imagined as a solid dome separating the waters above from the waters below. While scientifically incorrect as a physical dome, this concept remarkably parallels our modern understanding of the ionosphere, a boundary layer that separates Earth's neutral atmosphere from the charged plasma of space. The ionosphere acts as an electrical boundary, a threshold that influences both charge distribution and the water cycle, making it a conceptual analog to the ancient firmament. Let's examine another fascinating domain where threshold phenomena appear: condensed matter physics. Consider excitons, bound pairs of electrons, and holes in semiconductors. At low temperatures, excitons can form a Bose-Einstein condensate, exhibiting a collective, coherent behavior. This is a clear threshold phenomenon. Below a critical temperature, the excitons behave as an incoherent gas, but once the temperature drops below the threshold, they suddenly switch on to a coherent state, perfectly modeled by our logistic function. One of the most intriguing aspects of threshold phenomena is their role in theories attempting to unify fundamental forces. The concept of resonance appears repeatedly as a mechanism for amplifying microscopic interactions into macroscopic effects. Just like pushing a swing at the right frequency creates a large amplitude, certain physical systems can resonate when an external force matches their natural frequency. This principle has been applied to speculative theories linking gravity and electromagnetism, where gravitational waves might resonate with magnetic fields, amplifying their effect. Another example of a threshold phenomenon where a small input can trigger a large response. In conclusion, the logistic function serves as a powerful conceptual bridge across vastly different physical domains. From the quantum scale of the QCD mass gap to the atmospheric phenomena of Earth's global electric circuit to the condensed matter physics of excitons, we observe the same fundamental pattern: a nonlinear transition from one state to another at a critical threshold. The power of this analogy lies not in suggesting these phenomena share the same physical mechanism, but in providing a common mathematical language to describe emergent behavior across scales. By recognizing these shared patterns, researchers can generate new hypotheses and potentially discover deeper connections in the complex tapestry of the physical world. The next time you encounter a system that rapidly changes from one state to another, consider whether it might be modeled by the logistic function. Look for the critical threshold that triggers the transition, and consider the steepness parameter alpha that determines how abruptly the change occurs. This conceptual framework may help you see connections between phenomena that initially appear unrelated, leading to deeper insights about the fundamental patterns that govern our universe.